Okay, good morning. This is the last thing that we talk about, set theory here. That's a very simple lesson today. This is mainly about. Okay, so this is mainly about finite sets and the cardinality of them. So what do I mean here? So let us say that I have two finite sets. So let us say that A and B, these are finite sets. Okay, and then of course we can union them. Then I want to ask, how do you think the cardinality of the union relates itself to the cardinalities of A and B individually? Okay, so the naive guess might be that this is the case, yes? But it is clear that this is not always true. Yes, for example, if I give you the set A to be, for example, 1 and 2, and the set B to be 2 and 3, then if I ask you what the cardinality of A is, of course it is 2, the cardinality of B is 2 again, so this means the cardinality of A plus cardinality of B is 4. But here, if I ask you what is A union B is 1, 2, and 3. And if I ask you what the cardinality is, the cardinality is actually 3. And this number and that number are not equal. Because in this case, we have some common element in this case too. Okay, so I don't think it is hard to modify this in a way that it works. So how do you think I will modify the formula? Because this is so simple. For two sets, it is extremely simple. And in the book, you have gone up to 3 sets. That would be more interesting. And the book does not go beyond that. Okay, so the syllabus actually ends with 3 sets. But what do you think? How can I modify this? I mean, the best way to understand this is probably using a Venn diagram. Okay, if I have, this is the universal set, if I have 2 sets, maybe overlapping, then I have 3 distinct regions with here. Yeah, so I can call this region number 1, and I can call this region number 2, and then in the middle I have region number 3. Yes? So this is a good idea. If I ask you, what is the cardinality of A union B? I hope that you agree with me. It means the number of elements within this border. Yes? So because A union B is this, whatever inside this blue border is A union B. Yes? So if I ask you what is the cardinality of A union B, you will tell me probably the number of elements in region 1 plus the number of elements in region 2 plus the number of elements in region 3. By the way, this is a good method to visualize it, but my point is to write the right-hand side in a set theoretical language. Okay, this is not wrong at all, this is completely okay. But I want to write the right-hand side using the terminologies and notations used in set theory. Okay, so for example, here I can write 1, the number of elements in 1, plus the number of elements in 3. So I put this next to this one. And then instead of writing plus the number of elements in 2, I would write plus the number of elements in 2 plus the number of elements in 3. You will see why. And then, of course, I have to subtract the number of elements in 3. Yes? Do you agree? So the number of elements within the blue border is obviously the number of elements in region 1 plus the number of elements in region 2 plus the number of elements in region 3. I can rewrite this expression in this form, yes? 1, 2, 3, and then these 3 and minus 3 are gone. So I have 1, 2, and 3. Here I also have 1, 2, and 3. So that is correct. But what was the intention to do this? Because this will enable me to write the right-hand side in the language of set theory. That's it. Yes?
Can I give them back?
Pardon?
I think I know what it is. Like, be the cardinality of A plus B and then minus AB intersection.
Yeah, that's it. I'm just trying to motivate that for the harder situation that we have three sets involved, okay? Because in the first case, it was so trivial, you can even immediately guess. But the reason that I did that, because in set theory, I have a better language for this. What can I write for this? Yes, the cardinality of A, because this is the number of elements in 1, this is the number of elements in region 3, and then when I add them up, it becomes the total number of elements within A, which in the language of set theory, I can call it the cardinality of A. Yes? And I can do the same thing here. If I ask you what that is, this is the number of elements within the region 2, this is the number of elements within region 3. When I add them up, it becomes the total number of elements in region corresponding to the set B, which of course in this language of set theory, I can simply call it cardinality of A and B, cardinality of B, and then this number 3 is the number of elements within this region, but this region in set theory has a proper name, and that is called A intersection B, so I can write it as cardinality of A intersection B. So finally, so we can say that the cardinality of A union B is equal to the cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay? So some books, they move this to the other side, so they would say that the cardinality of A union B plus the cardinality of A intersection B is always equal to cardinality of A plus cardinality of B. But this is the version written in the book, so we will follow that. And then you see that the cardinality of A union B becomes sometimes equal to the cardinality of A plus B. But when does this happen? Yes? There is no intersection. This happens if and only if this part is 0. This part is 0. This happens if and only if the intersection is the empty set. Yes? So only under this condition, the naive guess that the cardinality of the union is the sum of the cardinalities is true. Otherwise, we have to use this formula. Okay, so for example, let me give you these type of word problems you need to be good at but they are very simple. For example, let me say that we have a classroom. Okay, in a classroom, the total number of students in a classroom is what? Let us say is 30. And then the number of students playing football so let us say this is 20, and the number of students playing basketball for example is 15. Okay, if every student in this class plays at least one game, one of these games, how many play both? How many do play both games? Yeah, something like that. I mean, yeah, of course this should be obvious. Yeah, so we have a classroom in which there are 30 students. We know that 20 of them play football, okay? And then 15 of them play basketball. If we assume that every student in this class plays at least one of these games, now how many do play both games? Yeah, it's 5, yes, but I mean, if you want to write it, so for example, let me denote let me denote the set of students playing football with capital F. This piece of information tells me that the cardinality of F is 20. Yes. And then let me denote by capital B the set of students who are playing basketball. And then this piece of information tells me that the cardinality of this set is what? 50. Because of this piece of information, every student in this class plays at least one of these games. So this means that the cardinality of F union B is what? Is 30. And then we are supposed to find the number of students playing both games. So it means that I want to see how many of them are members for both of these teams. Yes. So it means that I am looking for the cardinality of the intersection. Yes. And then you put them in the formula. So we know that the cardinality of F union B is equal to the cardinality of F plus the cardinality of B minus the cardinality of A intersection B. This number I know is 30. This number I know is 20. This number is 15. And this number is missing. Okay, so this becomes 30 is equal to 35 minus this cardinality. And as you said, exactly that this means this number is 5. Okay, yeah, it is not something very fun. Okay, but let us try to modify this formula for 3 sets. I want to more or less do the same thing. It becomes a little bit more complicated. So what is the question again? The question is that this time I have 3 sets, A, B, and C, finite sets. Yes? And the question is that how can I write a formula for the union of these 3 sets, the cardinality of the union of these 3 sets, so that on the right-hand side of this formula, I can use the language of set theory. Okay? Okay, I don't know, I can write the formula and then try to prove it, but let us try to explore it. And then, of course, we can convince ourselves that this is true. Yeah, we can explore it. So let me just, of course, we can prove it rigorously later, but let us at least use Venn diagram. The same idea I used for the simple case, I want to use this for this more complicated case. So when I have 3 sets, in general, I can have this scenario, yes? This is probably the most general picture or drawing that we can draw for this case. I'm considering all possibilities here by drawing the circles like that. And then, of course, let me name them. So I have a lot of regions now. So this is region number 1. Well, by region number 1, I mean this region. Yes? I'm trying to partition these two into disjoint partitions. Yes. So here, I don't know. Let me call this region region B. Let me call this region number 3, and then let me write this 4, 5, 6, and 7. Yes, is that understandable? So they don't have any overlaps in the way that I have named them. And then A union B union C is where? Is whatever is inside this border, this red border. Do you agree? So whatever is inside that red border is the number of elements within the red border is the answer to this. So in principle, It means that I have to write the number of elements in 1 plus the number of elements in 2 plus the number of elements in 3, number of elements in 4, 5, 6, and 7. Yes, so that is trivial. But the point is that even though this is completely correct, but this is the right-hand side is not expressed in terms of set theory language. Yes. Okay. So what should we do? For example, part A includes 1, 5, 7, and 4. Okay. So let us take 1, 4. 5 and 7 and put them next to each other. Okay, so what happens? So this is good, because at least instead of these 4, I can write simply the cardinality of A. Yes? So that is my goal. I don't know. You can also help me to see what to do. So here, 4, and then I have 5, and then I have what? 7. Okay, for this part, I don't have any problems. I can write cardinality of A. But there are more here, 1, 2, and 3. These are left. Okay, so where are these? 2 is here. 3 is here. Okay, and then 6 is here. Okay, so 2 and 6 are somehow related to B. Yes, but of course, for having the full B, I also need 4 and 7. But I do not have any extra 4 and 7. So what can we do? We can add them and take them off. So I can include them and exclude them. I'm intentionally using these words, okay? So I can do this. So I will continue. So I would write 2 with 6. Okay, so remember, I also used 2. I also used 6, so only 3 is left, and 3 will be somehow related to set C. Yes, so let us keep it like this. But then I have to add 2 regions to that. What are those regions if I want to have the cardinality of B? 4 and 7. So, but I do not have 4 and 7. I am adding them. So what should I do? To compensate for that, I have to take it off. So I include them and then exclude them. Okay? So don't get confused. So what is left for us for the time being? Only 3 is left. Yes? Agree with me? Okay. But then when I write 3, what should I write? 3 is doesn't have a good name here. But 3, 6, 7, and 5, in total, I can call them cardinality of C. So again, I include them, but because I don't have them, I have to immediately exclude them. Yes, are you following what I'm doing? Yeah. Yes, it's clear, okay? So then I would write 5, 6, 7. But then I have to exclude what I added. These are the ones that I have added. Okay. So let us see for which ones I do not have any problems for the time being. Do I have any problems here? No, I can express it as cardinality of what? A. So that's good. This one, B. This one,
cardinality of A intersection B.
Yes, is that right? Because 4 and 7 are these two together. So that is the cardinality of intersection and A and B. So far, so good. Do I have any problems here?
No.
No. That is cardinality of C. So the only problematic one is the cardinality of the last one. 5, 6, and 7. 5, 6, and 7. So this part. Of course, I can write it as intersection of these two and then union between them. But I can do a little bit better. So do you have any suggestions for me? So what do you think I will continue? I'm lazy to write everything down. I want to break it down here. Okay, so let's compare that one. What can I write, do you think? So for example, 5 and 6 and 7. 6 and 7 together has a good name. Yes? So let me separate them. So let me just do like that. How should I write it? So I would write it as minus 6 and 7 together. Okay? But this minus sign with that one becomes minus 6. Oh, sorry, minus 5. Okay. But then what do you think I will do? Yeah, we have to write something. Okay, we cannot be so lazy. Okay, so far this one also has a good name, 6 and 7. But what do you think I will do for 5? Yes, so I would write minus. I copy and paste this part. But instead of minus 5, which is alone, what do you think I would write? I would write 5 and 7. But what do you think I need to compensate for that? Add the 7. Because when I put a 7 here, there is a minus sign there. It means that I am excluding it. So I have to include 7 again. Yes? Is that right? So hopefully you agree with me with this kind of tricks. We are trying to understand what's going to happen. So I think now everything is in order. Yes? So what can I write for this one? This becomes cardinality of A. The second one is cardinality of B. Let us jump here. What is this one? Cardinality of C. You see 3, 5, 3, 5, 6, 7 is the cardinality of C. Okay? But now let us go and see here. Okay, so I considered this part, I considered this part, I considered this part. This is left for me now, which is 4 and 7 together, which is cardinality of which set? 4 and 7 is intersection of A and B, so it becomes minus intersection of A and B, the cardinality of the intersection of A and B. And then what are the things left? Don't get confused. This one, so here, this one is left, this one is left, and that one is left. Can I give this a name? 6 and 7 is cardinality of B and C, overlap of B and C. So that is good. This one has a name, C and A. This has a name, all of them. Yes, so this becomes plus intersection of A, B, and C, and that's the formula. Okay, and then these formulas are special cases of what we call inclusion and exclusion formulas. So the reason that is called like that, because as you realize, for understanding what is going on, we have to include and then immediately exclude so that we have the right number of elements involved in both cases. Oh, at least this picture motivates that this is a correct formula. That might be a correct formula, okay? So cardinality of A union B union C is equal to the cardinality of A plus cardinality of B, cardinality of C, minus cardinality of A intersection B, minus cardinality of B intersection C, minus cardinality of C intersection A, I don't know, plus the intersection of all of them, the cardinality of the intersection of all of them. It seems to be true. But this is, of course, not a rigorous proof. Yeah, we can also prove it more rigorously. Okay, so let us just do that as well. My goal is to prove this one using the case for 2 sets. Okay, for 2 sets, I want to use the formula up there, which is for 2 sets, and use that formula to prove this part, if this one is also true. Okay, that is my goal. Okay, so in order to do that, if you don't mind, let me write this formula up there in this form. the cardinality of two sets. Whatever inside the box is a set, whatever inside the circle is a set. But if I ask you what is the cardinality of the box union the circle, you will tell me it's the cardinality of the first set, whatever that is, plus the cardinality of the second set, but minus the cardinality of intersection these two sets. I want to use this blue formula to prove this one for you. So how can we do that? This formula works for the union of two sets, but I need a formula for the union of three sets. Yes, Afsh?
You can write the union of B and C as one.
One. Yes. So you can do that. Yes. So it means that let us try to do it here. Oops. Okay, so let us try to do this. So I will start from the left-hand side here. Yes. So I would say that A union B union C, even though this is the union of three sets, but I can call this one the box. Yes, and then I will consider this one my circle. So what can I do now? I can immediately use the formula for two sets. So it becomes the cardinality of the first one plus the cardinality of the second one, but minus what? Minus the cardinality of, what should I write inside there? Yes?
A intersects with B union C.
Yes. Any questions so far? So I am using this blue one to rewrite this one in this form. Okay? But again, for this one, what can I use? This is the cardinality of the union of two sets again, and I already can use the blue formula once again here. But the problem is here. Do you have any suggestions for me here? Because this is the cardinality of the intersection of a set A and the union. Can I write this intersection as union of two sets? So let us not jump ahead. So the cardinality of B union C can be written as what? According to the same formula. It becomes the cardinality of B plus cardinality of C minus the cardinality of B intersection C. So I don't have any problems with that part. But this one is intersection. Can I write this intersection as union of two sets in some way? Because if I can write it as union of two sets, then I can use again the blue formula once more. Yes? Distribution. So you know that A intersection B union C can be written as what? A intersect with B, A intersect with C, and then between them a union. So this is even though this is an intersection, but it can be written as the union of two sets. Okay. So then, if I ask you what is the cardinality of this, because this set and that set are equal, the cardinality of the left will matches with the cardinality of the right. So it becomes A intersection B union A intersection C. But now, can I use this blue formula once more here? Yes, because this is again the union of two sets. But I have to give the role of the box to this one in my head and give the role of the circle to this one. So if you help me, what should I write now in front of it? So it becomes the cardinality of what? A intersect B plus the cardinality of A intersect C, but minus the cardinality of
A intersects B union.
not union. Yes, because the formula tells you that this should be intersection. Yes, so I have to put intersection between the box and the circle. So it becomes the cardinality of A intersection B, A intersection C, and then intersect. Yes? Is that right? Okay, But can I simplify this? Yes, because all of them are intersections, so distributivity is not involved. But I can interchange them if I want to because of commutativity, and I can regroup them because of associativity. Yeah, so what can I do? I can write it as A, and A, I will take them together, and then I would take B and C together. But can I simplify it a little bit more? Yes, because A intersection A is what? A itself. Okay, so it becomes A intersection B intersection C. Do I need pair of brackets? No, because of associativity. Yes, it does. It is not ambiguous, so it becomes A intersection B intersection C. Okay, so everything is in order. So if I go back here, what happens? It becomes intersection B. A intersection B, cardinality of A intersection C minus cardinality. What do you think I will write here? A intersects B intersection C. Yes. So now everything is in order. If you don't mind, let us put everything back here in this formula. So the question mark that we have, so the question mark becomes what? The cardinality of A plus, instead of this part, I write this one. Yes? And then minus this one. But I have already calculated that one. This is in front of you. But I have to multiply this by a minus sign. But when I multiply this by a minus sign will go here, here, and there. So this one becomes negative, this one becomes negative, but this one becomes positive. Yeah, so it becomes minus A intersection B minus A intersection C, and then plus A intersection B intersection C. Yes, is that understandable? So this is a rigorous proof of that. If we, of course, take the one for two cases more or less so simple that I hope that you agree with me that's the correct way of proving it. But do you see, first of all, can you generalize it? Generalization is hard. Can you write the formula? Can you have an intuition for what is going on for 4 sets? Because by the way, for 4 sets, the method that I used up there is very tedious and probably not that efficient at all. First of all, because we don't know how to draw them. Drawing circles so that every pair of them intersect is not that easy. Yes, I don't know if you want to draw another. Of course, you don't have to draw a circle. You can draw an irregular shape, but the general idea is that we want to have pairwise intersections between our sets to consider the most general possible case. Okay, so and then drawing the Venn diagram for more number of sets becomes more involved and tedious. Yes. Okay, but first of all, let me test your intuition. You have the formula for 2 sets. You have the formula for 3 sets. Now, do you have an intuition for how the formula for 4 sets look like? Okay. Yes. So let me just write 4 sets. Let us assume that all of them are finite sets, and then I have these. So what is your intuition?
My intuition says that the cardinality of A union B means union B.
Not union. You mean what?
And cardinality A plus cardinality B plus cardinality of C plus cardinality of D
Yes. So far so good. Then
minus cardinality of A and D minus cardinality of A and C minus cardinality of A and D minus cardinality of B and C minus cardinality of B and D and minus cardinality of C and D and that's all, and plus cardinality of A, B, C, and D.
Intersection?
Yeah.
Okay, so that was his intuition. Another intuition. Yes, Rasmus?
I don't know if you can really call it intuition, but it would be very nice if it was just like then you add up like all the, instead of just adding one of the intersection.
Yes?
All three, you just add in the intersection of all pair or triplets of sets. And you
Yes.
subtract the triplets.
Yes, do you feel what he's saying? He's saying that, okay, in the case of two sets, we have the cardinality of B and C minus the intersection, the cardinality of every pair. But of course, in this case, we have only one pair. Yes? But for the second one, we have the cardinality of them individually minus the cardinality of every pair, but plus the cardinality of every triplet. But of course, we have only one triplet here. Yes? So might be this is a better intuition, yes? So we want to do the same here. So now that we have four sets, we consider them individually, we consider them pairwise, and then we consider them three at a time, and then we consider them four at a time. Yes? So, and then of course you also, I want you to, okay, now can you fix it, what is coming next? And then do you also agree with the plus sign?
Well, the triplet should be positive.
Yes, the triplets should be positive in this case. How many triplets are there? So we have to write all of them. It becomes the cardinality of A intersection B intersection C. And then
A intersection and B.
B and D, for example.
Yep.
And then
A intersection C and D.
yes. Is there any other triplet?
Yep.
Yes.
A B intersection C and D.
Yes. And the triplets are finished here. Yes, there are no more triplets. And then we go to the last one, which is consider four of them. How many of them are there? One. So then I would write this.
That would be minus one.
And then this one should be minus. So I hope that you have an intuition, at least this is, because I don't know, Rasmus, you told that's not intuition, but it was intuitive, yes? So here, this is the correct formula. For if we go to the four sets. And of course, what I did in rigorous proof, for the case of three sets, I used the case for two sets. So it reminds you of which method of proof in general. Induction, yes? Because when you want to prove the case for three sets, you use the previous step, which was the case for two sets. And of course, you can also do the same thing here.
So is that the more rigorous proof for the
No, the more rigorous proof might be, I don't know if we can talk about the more rigorous. You can, yes, if you can succeed to prove it using mathematical induction, which probably is a horrible task to do. Yes, you probably be able to do that. No, it's not a horrible task. I haven't checked that myself, by the way. Yes. We can test it. I haven't tested that myself. But in principle, because whenever you prove the next stage with the help of the previous stage, and then of course, and the statement is regarding a natural number, then of course everything indicates that maybe induction is a good method. But what is the natural number involved? Because I told you that for the induction to work, we need a natural number to do the induction on that natural number. What's the natural number here? If you want to, let us say we want to prove this using mathematical induction, we should have a statement regarding a natural number in order to be able to even set up my induction. Yes? No, what is the natural number? Because no, the natural number in the induction. So induction is useful for proving statements regarding natural numbers. Okay, what is the natural number here? We want to prove it in general case. This. So what is that n?
Do you mean starting from which?
No, I'm just saying this is a very meaningful question. If you want to prove this using mathematical induction, induction on what? Yes?
Using the number of elements or number of sets.
The number of sets. The number of sets. Yes? For example, when I want to prove it for the general case, it means that if I have how many sets? N sets. And I want to find a formula for this. This intuition is useful because you know that what is the weakness of mathematical induction? The weakness of mathematical induction is that you have to have the formula in its entirety. Okay? So that intuition is useful because you understand what is probably going on and claim this is true and then try to prove it. Okay? It's also, if you want, I can write it for you. By the way, how do you write the general formula? That's a very good exercise in writing mathematics. So you know what is going on. Okay? So how do you write it in a compact form? It is not a compact. I mean, write it. Yeah, write it. So what you wrote here for 4 sets, I want you to write it for n sets. I start with a sigma, yes? So what should I write? Sigma of what? So you know what is going on. The sum of every single set. The cardinality of A1 plus the cardinality of A2 plus the cardinality of A3 up to the cardinality of AN. Yes? So what should I write? Sigma cardinality of AI. I goes from what? From 1 to n. Yes? Okay. This is the first thing. But you know what is coming next because of your intuition. Your intuition was correct. So what's coming next? It's again, okay, all of them have a minus sign. So if you don't mind, let me factor a minus sign out and write minus. And then I have a bunch of terms added instead of being subtracted. So again, it becomes another sigma. Yes? So another sigma, what do you think I will write here? So what should I write? Yes?
A, I,
Uh-huh.
intersection A, I plus 1.
No, not plus 1, because A plus 1 works here. But A and C have 2 steps ahead. Yeah, one of them is 2 steps in front of the other one. So you have to consider all pairs. And there is a trick to how to write it. First of all, if you don't mind, let me write this I1. So it might help you. And then I will write I1 here. I1 goes from 1 to n. Okay? Then I would write I1 here. And then what? I2. Yes, I2. Okay? But how many sigmas do I need?
N.
No, here, only for this case.
Wait, how have we cryptographed do we have...
No, this one I have the cardinality.
Yes, but the first sigma, does that extend to be...
No, it's finished, right?
is
No, this sigma is finished here.
That's what.
okay. That's yeah.
Yes, that sigma is finished here. And then I have a minus sign. And then I have a sigma, intersection of every pair. Every pair, but not repeated pairs. Yes? So how should I write in principle? Okay, I would write a sigma for taking care of the index I number 1. And I also have to take care another sigma, yes, for taking care of I2. And then I would write AI1 intersection A, I don't know, so this is completely optional, okay? And then I run I1 from 1 to n, I2 from 1 to n. How many of you agree with this notation? No, let us, because this is mathematics, this is not social science. Is it true or false?
False.
False. And why is false?
Because both of them can go from 1. Or
Okay, so what's the problem with that?
because that would be A intersecting A.
So A1
A1.
intersecting A1 itself, which is not included, yes? So this is not a good symbol, the rotation. So how can I fix that? This is the way, might be you don't have that experience. This is the way that you write it in notation. You write A1 is strictly less than I2. Okay, and then you write greater than or equal to 1, less than or equal to n. Then it will take care of that none of them is repeated, yes? So if I consider A1, A2, I will not consider A2 and A1 again. I have to, because of this, what I put here. This is this, if you see a math book, they are writing this, it means that first of all, there are 2 sigmas, they write it only with 1 sigma. And then below that, they put I1 and I2, and then 1 and n is the range of these indices, and then by this constraint, they are telling you that A1 should be always less than I2.
You have to write an n above the sigma.
What then? No, you don't need, that's the point. You don't put anything on top. Yes?
Are we really allowed to reuse I1?
Yeah, here yes, we are, because that's a different term. Yes. So you see, let me just make it more clear. I'm just doing it for fun, okay? That's not something you really want to know. Okay, can you tell me what's coming next? The next one would be a plus. There will be a sigma. But how many sigmas are there in total? 3 sigmas, but we are lazy, we write it once. And then what do you think I will put here? I would write A, equip it with one index I1, and then A I2, and then A I3, and then intersect them. Yes? And what do I write below? 1 is less than or equal to I1, is strictly less than I2, strictly less than I3, less than or equal to n. Yes?
So you need an n amount of sigmas. This way.
There are n number of sigmas. One sigma is only dealing with I1. The second sigma is dealing with I2. The third one is dealing with I sub 3. The total range for all of them is from 1 to n, but there is also a restriction. In principle, I1 really freely can go from 1 to n. Okay? But when it comes to I2, because already I1 is set up, is assigned, so you are not allowed to have I2 below that chosen I1. Okay? Yeah, you need to think about it a little bit. Okay, but the interesting point is that, okay, we want to finalize the formula. So, what is coming next? Positive, negative, positive. So what is coming next? Negative. And of course, this is not fun to write for 4 of them because you already know what to do. The fun part is that we want to continue and finalize and finish the formula. Okay, finish it up.
So it's
Another question.
Yes.
Do you write n on top of the second?
No, we don't write.
Okay.
So here, this is taking care of the upper limit in this case. So be careful. Is the question clear? Because you start, now you understand what is going on. You have to repeat this process, and at some point the formula should end. Yes, Simon, this.
Okay, this is a complete and utter guess how we're supposed to finish it. But the last term
Now, what do you think I will put here first?
uh, s- dot
dot dot dot. Yes. Okay.
And then the last term should be. Now you have to correct me if I'm wrong, but negative 1 to the power of 1 plus n sigma.
Okay. So yeah. So I would write. So like this is not acceptable. I need something here. What plus? Yes. Good.
Sorry.
Okay. And then
1 plus n.
1 plus 8. I don't know. I have to check it myself.
To the power of 1 plus n. Then we begin the sigma.
No. Be careful.
No. What?
No, you shouldn't start the sigma. What is the last term? How many terms are in the last one?
N term.
There is only one. And including all the sets. There is no sigma left. Do you understand what's meaning? So here, when I have 3 sets, how many of the triple intersections I had? Only one. When I have 4 sets, I have only one. So there is no sigma left for you if you like sigmas. But this you get disappointed at the very last one. So the formula will be what? The formula will be intersection of A1, A2, up to what? AN. Okay? But let me check if what Simon said is correct or not. So how should I check that? For the case of 2 sets, the last sign is negative. For 3 sets, the last sign is positive. For 4 sets, the last one is negative. Yes? So I think you see the pattern for the sign of the last one. Yes? So I think you said it correctly, yes? Yes, n plus 1 is correct. Yes. Because what? Because I want to have, if it is 2, I want to have it negative. So you see, this formula was wrong. Because if n is 2, the last one becomes positive, which is wrong. So this is why actually Simon added 1 to it. Yes? So that's correct. But you missed the sigma part. Yes. Yes.
Is there a shorter way to write that?
No. At least I haven't seen that. And when I was writing it in, because I also needed to write something like this in my thesis, and I really care about beauty, the bad point about this, I try to find a lot of ways that people have suggested, because when you write this by LaTeX, the stupid thing is that, of course that's not stupid, LaTeX start this one at the very end of that one. And the distance between the sigma and this term becomes bigger and bigger, so it's ugly. Okay, so I remember I tried to fix it some way, and I think it looked more beautiful to my eyes at least. But anyway, you can test it. That's also a different story. Yes.
I mean, couldn't we technically write the last term as a sigma? No.
In principle, yes, but that sigma contains only one sigma. It is like that I have this. If I say you an, you can write it sigma I goes from n to n, of course. Yeah, something like that. That's a sigma, but you don't use the sigma there. Okay, so that's just, I wanted to, at least you learn how to write things, okay? So this is the most general formula that you can have, and this is called the inclusion-exclusion formula.
So, but,
The most general, yes.
so in the second and third sigma, it essentially takes the first sigma, like the I1 from the first sigma, and says, okay, I'm going to iterate.
No, that is, I don't want you to confuse. This I1 has nothing to do with that.
No,
I1.
no,
Yes, because I am considering this finished, and then I have started a new. Okay.
but we use the same notation.
It doesn't matter here.
Yeah.
Yes. For sigmas, because sigma variables are dummies, so it doesn't matter if you change the variables. Yes.
For the dot dot dots, before we had first one positive sigma and one negative sigma.
It does here.
Yeah. So
Yes.
how is it clear that the sigmas are in turn positive and negative?
This is taking care of that. Yes.
Not really.
Yeah, it is. Why not? Might be you are right. I don't know. So this means that minus. So plus minus plus minus.
Yes.
It indicates that this pattern, because dot 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 means I am telling you that the pattern will continue. Okay? And then if the pattern continues, because that's the only usage of dot dot. If you don't want to use that, then you have to write it. And your question might be is that, can I write the whole expression as another sigma?
Yeah.
I haven't thought about that, but might be that's possible. If you want to get rid of ambiguity, then what you mean is that, because that at the end is a sum, okay? But now, can I write this sum putting inside another sigma so that when I expand that sigma, it gives me this? You can think about it, but it should, in principle, it should be possible. Yes? No, why not? It should be possible. And the idea is that actually, let us write it. Because now what you said is actually what you are telling me is, yeah, what Rasmus said is that what is this one? Might be, I haven't checked that, I don't know if, but this might be a little bit fun. So how can I write this as 1 sigma?
Sigma.
So I can write it sigma 1 less than or equal to I1 less than or equal to less than I2 less than up to IN. Then I don't know how to, because this is also another 3 dots that I have to take care of. Yes, because there are 3 dots involved, and it makes it harder. Because 1 3 dot is here, somehow we can fix it. But what do you think about these 3 dots? Okay, I don't know. So then I can write it as less than or equal to n, and then I would write it AI1 intersection AI2 intersection IIN. Okay, so this can be written in that form. Okay. No, I don't know exactly, because then you can write another sigma, so then I have to bring a new counter counting the number of indices. Yes, can we write that? Yes, we can write a sigma. So we can write -1 to the power of, let me bring the sigma counter j. Yes.
Multiple counters in one sigma.
And then there will be another sigma here. But then I will have cardinality of AI1 intersection up to AI but index j. Yes. And then I have, this is the problematic part. So 1 less than I1 strictly less than I2 less than j less than or equal to n, and j runs from 1 to n again.
Is that
I think it is correct, isn't it?
sure?
Yeah, so if you want to, I can put the pair of brackets here. Yeah, it is correct, I think.
Can 1 sigma have multiple counters?
Now, here I have n sigmas, another sigma there, n plus 1 sigmas.
Yeah, but that's just a question. Can you have a sigma with more than 1 counter, or is it always just 1 counter?
No, every sigma should have 1 counter. Yes. I think it works, isn't it? For example, let us test. First, I choose j equal to 1. So j is 1. When j is 1, this becomes positive 1. Okay, so that's so far so good. J is 1, so these dots will end at the very first. And this will also end at the very first. Then I will have my first term. Yes? When I go to the second term, I put j equals to 2. That becomes negative. So that's correct. And then j is 2. So it means that this sequence goes up to I number 2. And then this also goes I1 and I2. Yeah, that's correct. But it is not that useful, you know. This method is also telling you the intuition behind it. But when you look at that formula, I haven't seen that formula. This is the first time I'm doing it myself. Okay, but anyway, I think that's correct, if you like it. But for coding, might be that's a good thing. Because if you want to write formula in general, then you have to do it. Any questions? Oh, it was complete deviation from what we were supposed to do. Okay. Anyway, Okay, let me also tell you a different method for proving this. It's combinatorial proof. We will start combinatorics, which is the most fascinating subject in this book later. But let me try to understand how they prove this in general. And that's extremely simple. Okay? It's not mathematical induction. So, for example, in the universal set, I don't know how to draw those pictures, but I imagine that I have the universal set. And then let us consider, I'm just imagining I have a lot of circles here. I have 4 circles, for example. I don't know how to draw them properly, but let us ask you some question. If I pick a point x in the universal set, there are some conditions for you. Either this x does not belong to any of them, or it belongs to exactly one of them, or it belongs exactly to 2 of them, or it belongs exactly to 3 of them, or it belongs to exactly 4 of them. Do you agree? Please, I'm just telling, I don't remember exactly what I'm telling, but I want you to fix me if I'm wrong. My question is that, let us try to imagine that I have a universal set, and I have 4 sets involved. Okay? This method, you can immediately prove this without induction, if I am right. So what you say is that I pick an element from my universal set. Okay? Do you agree with me that for this element that I pick up, there are some cases, 5 cases. Either this x does not belong to any one of them, or it belongs to exactly one of them, or it belongs to exactly 2 of them, or it belongs to exactly 3 of them, or it belongs to exactly 4 of them. Do you agree with me? Yes or no? Okay. So now tell me, if x does not belong to any of them, the case number 1, how many times this one element is counted here? 0. Do you agree? So that particular x is not considered even once on the left side. And I want to show you that on the right side, you don't consider that x at all. Why? So how many times it appears here?
0.
How many times?
0 times. 0 times.
0 times, yes? How many times it appears here, 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 0 times? How many times it appears here, 0, 0? So that particular x is not counted on the left side. It's also not counted on the right side. But things becomes more interesting. If x belongs to exactly one of them, how many times it is counted on the left side? Imagine that x belongs to exactly one of them, say A. Okay? So how many times it is counted here? Once. Do you agree? Because if it is exactly in A, nothing else, nowhere else, it appears in this union exactly once. Yes? So on the left side now you have 1. But now can you tell me what can I write on top of this? I don't know that x belongs to which one of them, but I know it belongs to exactly one of them. Okay? If that one is A, this is 1, this is 0, this is 0, this is 0. Or if this is B, this is 1, the others are 0. But in total, how many times it appears here? 1. Okay? But how many times it appears in the pairwise ones?
0.
Yes, 0. Do you agree or not? Because it does not belong, it belongs to exactly one set. Yes? So it does not appear in any one of them. And it does not appear in any one of them, none of them. So 1, 1 again. Is that right? Is that right? Okay. Now let us consider the interesting ones a little bit. Let us consider that x belongs to exactly 2 sets. Okay? How many times it appears here? In exactly 2 sets.
Oh,
How many times? It appears once, yes? But how many times it appears here? 2 times, because I don't know which one of these two are there, but there are 2 of them. Okay, so it becomes 2. But in how many of them disappear? 1 of them, because I said exactly 2. Let us say that pair is A, set A and set B. For example, then this one becomes 1, the other ones become 0. Or if that pair is A and C, this one becomes 1, the other one becomes 0. So in principle, in this one, it appears only once. Yes? Okay? But what about these ones? 0. And what about that one? 0. Okay, now look. On the left-hand side, it was counted once. In this part, that x is counted 2 times. But in this part, it is counted 1 time, but these are negative. So then the right-hand side again becomes 1 time. So it means that it is much easier. You see, it is not proving using mathematical formulas, working with these horrible formulas. You're just counting the number of elements that appear this time and that. Yes? Is that clear? So you can convince yourself about that. Let us go to the next one to test your understanding. If that's x belongs to exactly 3, can you count them properly now? Let us say that this x belongs to exactly 3 of them. So how many times I will count it on the left? Again 1. Yes? But what is this number now? It becomes 3. Okay, now can you tell me what should I write on top of that?
3,
Why?
because it will appear in 3 different locations. Since there are 3 numbers, there are 3 possible combinations of 2 numbers.
Yeah, that is correct. Yes. So I know that this set belongs. For example, it belongs to A, B, and C. For example, if I have A intersection B, I count it once. If it appears in this one, it also appears in this one. Yes. So how many of these pairs we have? 1, 2, 3, 4, 5, 6. But only 3 of them will matter. Yes. So it will appear 3 times here. Yes. But can you tell me about this part? It becomes 1. Yes. And how many times it appear here? 0. But is it correct again? It was counted once here. 3 minus 3 plus 1 is again 1. So this is a very elegant proof. You see, it is just counting the numbers 1 and 2 and 3, something like that. But you are proving this horrible formula in a rigorous way by counting things. Yes.
But if you would want to write this as a proof,
No, think about it.
Yeah.
Yes, you can do that. It is not hard. But of course, then you need the language of combinatorics we haven't studied yet. But the essence of the proof is exactly what I told you. Yes? And then let us finalize this. If I have that exactly in 4 sets, what will happen? Exactly 4 sets. It appears how many times here? 1. How many times here? 4. How many times here? 6. How many times there? 4. Yes? And how many times here? Once. So 4 minus 6 is minus 2 plus 1 and then minus 1. It's wrong. So let me write it. 4 minus 6 plus 4 minus 1. Is that right?
it's minus 2.
Yes. Yes, that's correct. It's 1 again. Yes? So that is the idea of proving these things general in a completely different setup. This is called combinatorial proof. We will talk about this later. When do you think we will finish?
30.
Oh, 30. Okay, so unfortunately we lost track of time. So there is a little bit, there is a good question in the book. So let me just immediately solve that and we are done. So none of these things that I talked is related to your course, okay? But let me, okay, so there is a problem in the book. Let me just do it very fast. So 2-1-31. And my Swedish is not good, but I try to understand what's going on. So there are 86 teachers. The number of teachers is 86. And the teachers are either tired, thirsty, or hungry. Okay? So And by the way, this is a little bit true. Okay, so the number of hungry teachers. So what is that? So can you read it for me? I should have my glasses with me. So this problem 21, 31.
131, okay.
Yes. The number of teachers are 86, but then
There are 31 tired teachers.
30 tired.
Yeah.
31
There are 33 thirsty teachers.
thirsty.
And
30 what?
33.
33 hungry.
37.
37.
Yeah.
And then
Among these 11 teachers are both hungry and tired.
so hungry and tired is what?
11.
11. Number of
Both thirsty and hungry.
thirsty and hungry
There are 7.
and hungry. 7.
Yes, 7.
Okay, and then number of
6 teachers are tired and thirsty.
tired and thirsty. How many?
6.
6.
And then 5 teachers are all of them.
All of them, okay. So they have to quit probably.
Yeah.
So all is what? How many?
5.
5. Okay, so this is the information given to you. And then you are supposed to answer which questions? So number 1, the number of teachers that are only hungry. Okay, so you might think that it's a good idea to use the formulas. I don't like that method. Okay, so the Venn diagram, because in your book you go up to at most 3 sets, it is always better to use Venn diagram. Okay, so if you don't mind, for tired, let me write T. For thirsty, okay, that's a little bit unfortunate. Let me use little t, even though it's a little bit deviation from a standard notation. And for this one, let me consider hungry H. Okay? We want to find the only hungry one. Of course, you can manipulate the formulas, but if I myself want to solve this problem, I try to use Venn diagram in the way that I've tried to describe. So I would write the whole number of teachers, so the rectangle, the universal set containing all the teachers. So I have a tired part with capital T, I have a thirsty part, and I have a hungry part. Okay? Instead of writing so many formulas, I would try to do like this. I start with this piece of information. Oh, I forgot to write the okay, all of them is 5. So where is 5? 5 number is here. Yes? This is a better way instead of using the formulas. Okay, and then I go back here. Tired and thirsty should be 6. This is tired and thirsty. This part should be 6. But 5 of them are already there. So what is left for this part? 1. Yes? Again. So 5 is all of them. So when you say all, it means this is the intersection of all of them. This part is 5. And then I go backward here. Thirsty and hungry teachers should be 7. Thirsty is here. Hungry is here. This is the overlap.
Thirsty is little t.
Thirsty is little t. Yes. Yes, this is the little t.
Yes.
Okay, so now what should I do now here? So thirsty and hungry.
No, it's the other.
Okay, so you are okay. So hungry and tired. This is tired and hungry. Is 11.
Yeah.
5 of them are there. So what is left here? 6. And thirsty and hungry is 7. 5 of them are there. So what is left here? 2. It's much better way to do it. And then go to the tired part. The tired part is to be 31. So it means the whole circle of tired should include 31 teachers, but this is how many of them? 12 of them. So what is left here? 90. And what is left here in the thirsty one? The thirsty one is 33. So how many of them are here? Is 25. Because 2 plus 7, 8. And then minus that one is 25. And hungry teachers are what? 37. And then 2, 5, and 6. How much is that? 13. It's 24. Yes? So you really don't need to memorize any formulas, anything. That's much better. Okay, and in your book, we have at most 3 sets. So this is the best way to do it. Okay, now can you answer me part A? What is the meaning of the number of teachers that are only hungry? So the only hungry one means the 1, 24. Is that right? This is the number of teachers who are only hungry. These are these parts. So the answer to that part is just 24. Is that clear? Okay. What is the second part?
The second question was how many teachers are only tired?
Only tired. We already answered that. It's 19. Yes?
The last question is how many teachers are neither tired, thirsty, or hungry?
So how do you answer that question?
We add all the numbers we've written inside of
The circles?
yes, and then we subtract 86 from it.
Yes. Because we want to see how, which teachers we have to raise the salary for them, yes? So then we need to know how many people are out there, yes? Of course. And then you add these numbers. Can you see what that number is? So 49, 51, and then 57, 65, 63, and 82.
Yeah, 82.
Yes. So 4 is left out. So these teachers are neither hungry, nor thirsty, nor tired. Might be, for example, in the exam, I can ask you what you pick up a teacher in random. What is the probability that that teacher is neither tired, thirsty, or hungry? Well, how can you calculate the probability? You say that, okay, the total number of elements is 86. The good teachers are 4. So we say that 4 over 86 is the probability that if you pick a teacher in random, that teacher is neither thirsty nor hungry nor tired. Yes? So you see, this is probably one of the good problems in the book. And then you will get these kinds of problems in the exam. At most with 3 sets. Yes? And I recommend you, don't try to memorize them, because the formulas I think are not in the formula sheet. So you don't need to memorize them. And then it is always better to draw the Venn diagram because you also understand what is going on. Any questions? Okay, thank you very much.